This week we're going to look at a topic that we haven't talked about in quite some time, which is CAPE, and we'll talk about some of the recent changes to the CAPE calculation in MetPy. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. This week I want to talk about something that you may say, that sounds familiar, and we have talked about CAPE in the past, but I want to focus on some of the changes to CAPE and remind us how to use the CAPE function correctly. All right, so first we're going to need to do our imports. MetPy.calc as mpcalc is our convention. From datetime, I'm going to import datetime. From MetPy.units, I'm going to import the units registry as well as the pandas data frame to unit arrays helper. And from siphon.simpleWebService.IowaState, I'm going to import the Iowa State upper air class. So obviously to do a calculation with CAPE, we're going to need some data. So the reason we're importing all of these things in Siphon is so we can go get some data to actually run these calculations on. Oh, it's the Iowa State upper air. There we go. Okay, so first of all, the date. I'm going to use a date time. Go back a day or two here, just so we're sure there's data there. We'll pick somewhere that's going to have a nice energetic sounding, like Miami, Florida. And using tab completion to help reduce those typos, I'm going to call the request data method for the date and our station. Also, I'm going to go ahead and save the units. Remember, we attach a units attribute to a data frame. I'm going to go ahead and save those off as df_units. So I have them handy as I modify my data frame. If you need a reminder what this data frame looks like, here it is. We have all the standard columns you would expect from a sounding. But I really want this as a united array, and I want to do some cleanup. As you see, there's some nans in here, and nans generally don't play well with calculations. So the first thing we're going to do is deal with the nans, and then we'll deal with the units. I'm going to use the drop NA method, and on the subset of pressure, temperature, and dew point. That'll make sure that we have those three fields that we're going to need to do our thermodynamics calculations in every row, and if they're not there, we'll drop them. Next, I'm going to have a data array using the pandas data frame to unit arrays helper with our data frame and the column units keyword we're going to set to df units. So as a reminder, what that does is create a dictionary in which the key is the variable name and the value is a united array. So an array with units attached. Okay, so now we're finally ready to start talking about CAPE. So our CAPE function is going to take the pressure, temperature, dew point, and a parcel profile, which means we need to calculate a parcel profile. Luckily, MetPy makes this easy with the parcel profile function. So I'm going to pass pressure. Then we need to specify a starting temperature, our surface temperature, and a starting dew point, our surface dew point. And that creates our parcel path. Finally, we're ready to calculate CAPE. As it turns out, this function is going to return CAPE and CIN. It is the CAPE CIN function. It is going to take pressure, temperature, dew point, and it's going to take our parcel path or profile. If we print out the results, we see that we've got 1947 joules per kilogram CAPE and about 45 CIN. Now, it matches relatively well with what's on the Storm Prediction Center website right now. So you might say, well, there's nothing different in this code. Why are we talking about CAPE and CIN again? Well, the main reason is, one, to remind ourselves how this works, but two, to let you know that we now use the virtual temperature correction when calculating CAPE and CIN. This was really briefly mentioned when we announced the MetPy 1.5 release, but somebody else had mentioned in the comments that they'd like to talk a little bit more about it. So the virtual temperature correction uses the virtual temperature instead of the environmental temperature when calculating CAPE and CIN. And why would we want to do that? Well, we know that the virtual temperature lets us use the dry equation of state on moist air parcels. And we know that as we add moisture to the parcel, it becomes more buoyant. So there's an effect known as vapor buoyancy, meaning that if we just use the environmental temperature, we're missing out on some of the buoyancy of the parcel, and therefore we would have lower values of CAPE than the parcel's actually going to have. So it's recommended by the AMS and a number of abstracts that the virtual temperature be used instead of the environmental temperature when calculating CAPE and CIN. So that's now what we're doing. This is a relatively minor change, but is important if you're using these calculations from previous versions and comparing them to calculations from newer versions. It's also helpful to keep in mind that when you have large values of CAPE, the relative error will be much smaller than when you have small values of CAPE from using the virtual temperature correction or not. Now, another reason that's a good time to talk about CAPE and CIN is let's go look at the documentation. So if you go to the MetPy documentation, which is unidata.github.io/MetPy, you're met with this page. You can click on the reference guide, which is where you need to go to find all things about how functions and methods work. Calculations. And let's scroll down here and find CAPE and CIN. So it's under soundings, CAPE CIN. If we click on this, we see there are also some new keyword arguments that you may not have seen before, and we certainly didn't talk about last time we had a video on CAPE or CIN. Which LFC and which EL. If we look in the documentation, we see that the which LFC says which LFC to integrate from. So remember, we're calculating CAPE as the area between the level of free convection and the equilibrium level. There can be multiple LFCs or ELs found in a given sounding. So by default, we use the lowest LFC and the highest EL. But you could also use the highest LFC, the lowest, wide, which means it's going to pick the LFC that gives the greatest separation between LFC and EL, or most CAPE, the LFC that result in the most CAPE. And all of those same options are present for the EL as well. So it's helpful to note there are these things that you can now modify about how the CAPE CIN calculation works, and helpful for you to know, especially if you're using it in research and working across multiple versions of MetPy, that now we are indeed using that virtual temperature correction. I hope that you found this useful, and I'll see you on next week's MetPy Monday.